have been discussing approximate molecular orbitals for homonuclear diatomics and center B. The axis passing through the centers is called z-axis, and we are using the linear combination of atomic orbital method. So far we have constructed molecular orbitals from 1s and 2s atomic orbitals centered on each nuclei, and we have what we call 1 sigma g, a constant, overall constant, which is a normalization constant. It has the form 1sa plus 1sb, and another molecular orbital constructed from the same atomic orbitals is 1sa minus 1sb. Similarly, from the 2s atomic orbitals, we have second sigma g, which is a constant times 2s on A plus 2s on B, and finally the relative energies of these orbitals are, if this is 1s energy, then this is the energy of the atomic 1s orbital for center A and for center B. That is also the same. This is first sigma g molecular orbital energy, and this is first sigma u star molecular orbital energy. Relative to the 1s atomic orbitals, one sigma g molecular orbital has a lower energy, and therefore it is bonding, whereas the 1 sigma u MO has a larger energy, higher energy relative to the atomic 1s orbital, and therefore it is an antibonding orbital. Now, the next set is 2s, similar to this one. This is 2sa, this is 2sb, and this is first sigma g, second sigma g here. And this is second sigma u star. So far, therefore, these are the first 4 molecular orbitals. 1, 2, 3, 4 molecular orbitals in order of energy, and their forms are seen here. Okay, Next, we construct molecular orbitals using the p-type atomic orbitals. Now, let us first define. This is the centers, A and B. There are three p atomic orbitals. These are px, py, and pz type atomic orbitals. You may imagine these are 2p orbitals. Okay, let's make it concrete. Two px, two py, and two pz. P-type atomic orbitals have directional properties. Therefore, we have to define exactly what we mean by pz, px, and py. Z-axis is selected, chosen as this line, which passes through the nuclear centers. X-axis is perpendicular to the z-axis. Say x-axis is this way, and y-axis is perpendicular to the blackboard. First, pz type atomic orbitals. This is a pz, 2pz atomic orbital centered on nucleus A. So the notation is that if this lobe has a positive sign, that lobe has a opposite sign, negative sign. Now, this is therefore a 2pz on center A. Is this my notation? Yes. Let us also sketch the 2pz atomic orbital centered on center B. This is 2pz centered on nucleus B. Okay. The pi type, from such atomic orbitals, we can construct only sigma type molecular orbitals. Let us discuss the general principle. We are classifying molecular orbitals in diatomic molecules according to the number of nodal planes. But these nodal planes are special planes in the sense that the plane must contain the molecular axis, the z-axis. And if we can find, if there are no nodal planes of this type, the molecular orbital will be called sigma. In other words, lambda values are 0, 1, 2, 3, etc. Letter codes which correspond to these are sigma, pi, delta, phi. lambda values also indicate number of nodal planes which contain the entire z-axis. Now, for a S-type, S atomic orbital, say on center A, has no such nodal plane. As a result, S atomic orbitals can only contribute to sigma type molecular orbital. Similarly, PZ atomic orbital, like such as this one, also doesn't have a nodal plane of the required type. So this is a PZ type atomic orbital on center A. Now, if you consider all planes which contain the z-axis, it is not possible to find a plane like this on which the PZ atomic orbital has 0 value everywhere. Therefore, PZ atomic orbitals also contribute to lambda equals 0, which means sigma type molecular orbital. On the other hand, this direction is, if this is z, this is x direction. So this orbital, atomic orbital, this is a px atomic orbital. You see that if you consider this plane, and this plane is the yz plane, on the yz plane, the atomic orbital has 0 value everywhere. So, and there is only one such plane you may find, which means a PZ type atomic orbital contributes to lambda equals 1, which means a pi type molecular orbital. So 2px, and same thing is true for 2py, because 2py is directed this way along the y direction. In that case, the xz plane is a nodal plane, and there is only one such nodal plane. 2px and 2py atomic orbitals contribute to pi type molecular orbitals. Whereas S type, whether it is 1s, 2s, doesn't matter, and PZ type atomic orbitals contribute only to sigma type molecular orbitals. Then now let us continue. So the form of the molecular orbital is a coefficient times 2pz on A plus another coefficient times 2pz on B. All right. Now here, because of the inversion center in a homonuclear diatomic molecule, we know that C1 will be equal to C2, or C1 will be equal to minus C2, just like the case for the 1 sigma g and 1 sigma g, 1 sigma u 2 sigma g, 2 sigma u star. We can say due to inversion symmetry. Now, the case for C1 equals C2 can be shown like if C1 is equal to C2, we have this molecular orbital, 2pz on A plus 2pz on B. Relative values of the coefficients are +1 and +1 times C1, both of them, but relative values are +1, +1. Now, we show or display this molecular orbital by such a diagram. And in redrawing this diagram after multiplying each atomic orbital with the relative values that you see here. So this atomic orbital is multiplied with +1 so that the graph doesn't change. This atomic orbital is also multiplied with +1. Therefore, the graph again doesn't change. But now, you should imagine addition that you see here. Adding value of 2pZa at a given point to 2pZ on center B at the same point. And imagine what will happen to the sum between the two nuclei. Because this atomic orbital has a positive sign between the two centers, whereas this atomic orbital has a negative sign between the two centers. There is, when we add them, the value of the molecular orbital will be small between the two nuclei, because this lobe has a positive sign, whereas this lobe has a negative sign. Now, if we compare this with the other case, C1 equals minus C2, let us draw it here. This is center A, this is center B. Now, in this case, the coefficients are minus. So the relative values of the coefficients is, if this is +1, the coefficient of this orbital is -1, which means this minus here. All right? So, we have this atomic orbital is multiplied with +1, but this atomic orbital is multiplied with -1, which causes the lobes to interchange. In other words, we have this like this, but after multiplication with -1, this side becomes minus, and this side becomes, this lobe becomes plus. So this is multiplied with -1. You take these independent atomic orbitals and multiply one of them with +1, the other with -1, and then redraw them, and then imagine this addition or subtraction. Okay. Now we are comparing this molecular orbital with this one. And the question is, which one has a lower energy? Which means which one is a bonding molecular orbital and which one is anti-bonding. we see that in this case, because the lobes between the two centers, this one and that one, has the same sign. When we add them, electron charge density will be larger between the two nuclei. Whereas in this case, there is a cancellation of values because this lobe has a positive value, this lobe has a negative value, and when you add, as in here, there is going to be cancellation of the value of molecular orbital at points between the two nuclei. Now, the general rule is that when you compare two molecular orbitals, the one with that has more electron charge density between the two nuclei has a lower energy, or it is bonding. So, when we compare these two, this has smaller charge density between the two centers, between the two nuclei, relative to that one. Therefore, we conclude that this molecular orbital is more bonding than that one, or this molecular orbital has a lower energy than that one, or this molecular orbital is bonding and this one is anti-bonding. Just using these principles about charge density between the two nuclei. As a result, both of these are sigma type molecular orbitals. Sigma in other words, we had so far first sigma, second sigma. These will provide the third sigma. In other words, the energies of these molecular orbitals will be higher than what you see here. So we are numbering them according to their energies. The lowest one is the first one, next one is second, the third one is third, and so on. Okay, next, let us put the star. Which one is, according to our discussion, when we compare the energies of this orbital with that one, which one is expected to have lower energy, which means bonding? The lower one or the upper one? Which of these molecular orbitals have smaller charge density between the two nuclei? Remember, this graph is for this MO, and that graph is for this MO. We have concluded that this molecular orbital has higher charge density, electron charge density than this one between points between the nuclear centers. Therefore, this orbital, this molecular orbital is expected to have lower energy than that one, which means the higher energy molecular orbital is antibonding. So we put a star. Please note that it is not always the case that the molecular orbital in which coefficients are all positive will give lower energy, because it depends on the definition of the atomic orbitals. Okay, next. These molecular orbitals should have gerade and ungerade property. This is the center of symmetry. Now take a point here, say that point. Now construct a line that passes through the inversion center and then extend it up to here. That distance is the same as that distance. Now compare the signs of the atomic orbitals at the initial point with that at the final point. In this graph, do you see, what do we see? Are the signs of the atomic orbitals at this point and at that point same or different? What do you see? Sign means plus or minus. At this point, the sign is plus. At that point, the sign is also plus. This point is the inverted point of that point. Therefore, under inversion, this molecular orbital has the same value. And when it has the same value under inversion, we call it gerade or ungerade. Gerade. Gerade corresponds to +1, ungerade corresponds to -1 with respect to inversion. So this is G-type. Which one is that one? It is this. So this is gerade. Now do the same thing for this orbital, which is the antibonding orbital. Take any point. Here is origin. Extend it. Pass a line or construct a line which passes through the center of symmetry and extend it to the other one. So compare the sign at this point with the sign at that point. What do you see? Here it is plus. Here at the inverted point, the sign is minus. As a result, we conclude that this molecular orbital has ungerade symmetry, U. Which one is that? It is this orbital. Now, their energies will be larger than the molecular orbitals constructed from 2s type atomic orbitals. Say, if this is atomic 2pz, this is 2pz on A, this is 2pz on B. We have a sigma type molecular or bonding type, and then antibonding type. Now, according to our labeling, this is the third sigma G, and this is the third sigma U star. Okay. These are the molecular orbitals. We can molecular orbitals of sigma type we may construct from. These are from 1s atomic orbitals. These are from 2s atomic orbitals. And these two are from 2pz atomic orbitals. All of them have sigma type, sigma property. Next, we construct pi type atomic orbitals because we have px atomic orbitals and also py. Now, first we draw the px, two px atomic orbitals on two centers separately. You see, both atomic orbitals have a nodal plane which contains the z-axis, and there is only one such nodal plane. So these will contribute to pi type. Pi means lambda equals 1, and lambda equals 1 means pi type molecular orbitals have just one nodal plane of this type, which must contain the z-axis. And here you see that both of these atomic orbitals contain just one such nodal plane. Now, this is 2px on center A. This is 2px on center B. A constant, a normalization constant. This is going to give us a pi type molecular orbital. Remember that this is the first time we encounter pi type molecular orbitals. Therefore, we will call this the first, number 1 pi. Now, there is another molecular orbital which has this form. But with a minus sign. This is also pi. Now let us first determine the parity of these two orbitals. The first one, let us use this graph. The first px on center A is multiplied with +1, and the other one is also multiplied with +1, and then added here. So if we do that here, now imagine this as this orbital is multiplied with +1, that orbital is multiplied also with +1, and then we are adding. Whereas this molecular orbital, let us also show it in a diagram. This is x direction. This is center A. This is center B. Here, the first orbital is multiplied with +1, just like there. So we show it this way. After multiplying with +1, we redraw it. The second atomic orbital is multiplied with -1 there. So there, the graph will be, after multiplication with -1, this side becomes minus, and that side becomes plus. So what will happen? This is after multiplying with -1, the original equation. Okay. First, Gerade-Ungerade symmetry. Take any point. Here is the inversion center, O. Now, draw a straight line and obtain the inverted point. Next, compare the signs. Here, at the initial point, the sign is plus. At the inverted point, the sign is minus. There is a sign change. Therefore, we conclude that this molecular orbital has Ungerade symmetry. Which one is that? The first one. Here we write U. If you do the same thing here, here is the origin. Take any point. And the inverted point. At the initial point, according to this diagram, the sign is minus, but at the inverted point, the sign is also minus, isn't it? There is no sign change. You could take any point. You could take a point in the upper lobe and then do the same thing, you will see that there is no change. It doesn't matter which point you take. There is no sign change, therefore we conclude this molecular orbital has gerade or ungerade symmetry, gerade. So this is, it is this molecular orbital, this has gerade symmetry. Next, we ask which one has lower energy. We are comparing just two molecular orbitals. And our principle is the same. The one that has larger electron density between the two nuclei is lower in energy. That's our principle. Now let us look. For this molecular orbital, this is 1 pi u. Just imagine adding, arithmetical addition, as you see here. Now, points between the two nuclei are points in this region. We see that when we add, electron charge density is concentrated above the z-axis and below the z-axis. Remember that charge density is proportional to square. Therefore, after adding, for instance, value of this orbital at points below the which plane? YZ plane, will have a negative value, but charge density is square. So charge density below and above will be same, because values at the lower part are just negatives of the values on the upper parts. So charge density is, that's one property of pi orbitals. Charge density is not largest at points along the molecular axis, but charge density is largest above and below the molecular axis. That's a characteristic of pi type molecular orbitals. Now, when we compare the charge density at such points or such points with this one, we see that here there is a subtraction. Because this lobe has a positive sign, that lobe has a negative sign. So when you add, according to what you see here, the charge density between the nuclei for this molecular orbital will be lower than charge density for that molecular orbital between the two nuclei. As a result, we conclude which one is bonding. We are comparing these two. Is this bonding or is that bonding? Which one? This one? Look, the principle is this. We are comparing just two things, all right? And then the question is, which one is expected to have lower energy? And the idea is the one that has more charge density, electron charge density between the two nuclei is lower in energy. In this case, this lobe has the same sign as that lobe. And when you add, according to this construction, there is some at least non-zero values at all points. But for this one, when you add, for instance, if you consider such a plane, which plane is this? This plane is XY plane, which is perpendicular to the blackboard. On this plane, at points on this plane, the sum of that plus that one will produce zero value. No such zero plane is present here. Therefore, charge density which is produced by this molecular orbital is larger than charge density that this molecular orbital gives. As a result, this molecular orbital is bonding, and this one is anti-bonding. Or which one is this? It is this one. So we put a star there to indicate that it is anti-bonding. In other words, this one has higher energy than this molecular orbital there. Now, let us look at this part once again. 2px on center A, atomic 2px on center A has the same energy as atomic 2pz on center A. And also there is 2py. This is 2px on center B. We have a molecular orbital of pi type, which is lower. It is the first pi. What was the parity? Pi u, which is bonding. And there is a anti-bonding 1 pi g. Remember that according to the lambda values, molecular orbitals with lambda equals 0 are non-degenerate. There is only one such molecular orbital. Because if you remember, definition of lambda is magnitude of m. Now, for pi-type molecular orbitals, lambda is 1. That means there are two values for m. One is +1, the other is -1. Same thing is for delta. Lambda is 2, there are just two values for m. One is +2, the other is -2. All these molecular orbitals are doubly degenerate, which means there must be two molecular orbitals with the same energy. Here's one of the molecular orbitals constructed from 2px type atomic orbitals. But if you rotate this diagram and that diagram by 90 degrees, you will obtain molecular orbitals constructed from 2py type atomic orbitals. Obviously, rotating the molecular orbital by 90 degrees does not change the energy. But because the direction is different, it's a different molecular orbital. In other words, we should draw here another dash. This is not there, here. This is 2py on A, and similarly here 2py on B. And there are actually how many molecular orbitals here? Bonding type, 2 type. The second molecular orbital of the bonding molecular orbital has this expression in which the X subscript is replaced with Y subscript. And same thing is true above. There are two pi antibonding pi type molecular orbitals. Maybe we should show this molecular orbitals also by just 2 dashes. These are constructed from 2px and 2py type molecular orbitals. So each molecular orbital is doubly degenerate. The next question is, the relative energies of the pi molecular orbitals relative to the molecular orbitals which are constructed from 2pz, because we know that atomic orbitals 2pz, 2px, and 2py have the same energy. All right? Now, the charge density argument does not help us in deciding whether 3 sigma g has a lower energy than 1 pi u or not. We have to do actual calculation. The result of the calculation shows that, first of all, the sigma, antibonding sigma constructed from 2pz has the highest energy. So the relative energies are like this. For the orbitals constructed from p-type. Now here we have px, py, pz on center A. Here we have px, py, pz on center B. Now, there are among these, the highest energy molecular orbital is 3 sigma u star. This is the result of calculation. Pi-type antibonding orbitals have lower energy than the 3rd sigma u star. This is, what was it? 1 pi g. This is also antibonding. Now, the bonding pi orbitals have lower energy than the atomic 2p energies. So this is 1 pi u. And relative order of the 3rd sigma g, according to calculations, for some diatomics on the constructed from 2nd row atoms, it could be either lower or higher than the pi u type orbitals, but mostly, for most of them, as I have indicated in the lecture notes, the pi energy is lower for most of the molecules, so we will use that. So relative order is, this is the bonding sigma type molecular orbital, which is 3 sigma g. So this is how they are represented by an energy level diagram. Now, these are 2p on A, 2p on B. Once again, all of these molecular orbitals have energies which are larger than the energies of the molecular orbitals constructed from 2s atomic orbitals. They are above. Among themselves, all of them are constructed from 2p type atomic orbitals on each center. There are 2 of them are sigma type, this one and that one. There are 4 molecular orbitals which are pi type. So you should imagine this picture to replace what you see here. Okay? So this one, which are above the 2s energies. So we give